This is ENGI 17900, Industrial Electronic Devices. This is Lab 2. So the first thing we want to do is to gather all the parts that we're going to require. So we have our breadboard, we have some resistors, and two pieces of component wire which we'll be using later on to connect some current. So the resistors we're using in this particular lab will be a 33 ohm resistor, a 47 ohm resistor, a 51 ohm resistor, an 82 ohm resistor, and finally a 100 ohm resistor. Okay, so step 2, now that we've got all of our resistors, and I have trimmed those leads so that they're close to the breadboard itself, I'm going to use the breadboard to hold these resistors as I take an actual measurement. So we're going to make sure that our meter is not set for continuity, that it has the screaming person icon gone. And we're just going to take it one step at a time. We're going to read across, wait till it settles down. And that says 33.4, 33.5 ohms. So I'm going to record that. And now I'm going to measure the next one. .3. And you will continue to do that for all 5 resistors, recording the amounts. Now before any measurements are taken, after the parts are assembled on the breadboard, you want to take the initial values, the nominal values, and add them up. I'm going to use this to make sure that we actually have a complete circuit. So step 3 is to construct our actual first circuit. I've made a couple of jumpers so that I can bring the red lead to the actual work surface. Then I go into this row here, through the resistor, into this row. Now it does not look like the drawing in as much as it's not a straight line of wiring, but inside we have to recall that a row is considered to be all at the same potential, therefore it's continuous. So we can move this to an offset by one row, through to the next row at the end, then through the back plane basically into our third resistor, into the back plane, out of the back plane, across our fourth resistor, into the back plane of the breadboard, out again, through our last resistor, in and then out through the jumper to complete the circuit. Now that we have the board arranged in the correct fashion, I'm going to do a test to see that we have continuity. On my meter, there is a small emblem above the horseshoe, or the omega sign, that looks like a series of sonar or sound waves or someone screaming. This tells me I'm on continuity. If I take my 2 leads, and in this particular model, the tester came with not only the class increasing protective shield for class 3 and 4 applications, but it has a class 2 fitting that has a bit of threads on it, and that's designed to take an Allen alligator clip that comes equipped with this particular meter. So this allows me to put on and thread on an alligator clip. I've done this with our black lead, and it's connected to the jumper, so that's going to give us a part of that circuit. Now, if I were to touch that to the black, I should get continuity. And as I work my way through, at some point it's going to stop. And that has to do with the construct of the meter itself. Although it is set to ohms and it's in continuity, at a certain point in time it's going to stop beeping. At that point, you will no longer get an audible signal that the circuit is complete. From experimentation, I have found that 50 ohms and lower, it will allow and continue to push through the circuit. But in a practical sense, after 50 ohms, it will not work. It will show you the resistance, not give you an audible sound. It's important to understand the limitations of your tools so that you're not listening for a sound, for example, when doing continuity, and when you discover later on that there was continuity after all when you thought there was not. So now that we know we have continuity there, we can go all the way to the other side and see if we can get a reading. And I'm getting a reading of around 313.2 ohms. Depending on whether or not this is a complete circuit, I will check that and compare that to the number that I added up. We're now going to apply power to our circuit. Keep in mind, once the power is flowing, the resistors are going to heat up. That's one of the three things that heaters do. I've set my meter to volts, but notice I have two choices. I have the wavy line and I have the flat line. I have to press my select button until it says I'm reading DC voltage. So I'm going to check my power source first, and I'm using a portable source. It's a 9-volt DC battery. I want to know the amount of voltage I'm beginning with in my experiment. Notice that one protrudes positively and one makes a hole. That identifies my positive and my negative. So I'm going to make my polarity correct. And right now this battery is producing 9.53 volts. So now I'm going to apply power to it. I've moved the leads still on my negative bus and my positive bus, just so that I can still have the meter in the view of the camera. I'm going to match the two leads and components. And now I should be applying about 9.5 volts overall through the circuit. So we're going to check by looking at the voltage between the beginning of our circuit and the end of our circuit. And we've noticed that there's been a bit of a power drop. That's to be expected on a DC battery. It will lose voltage as it begins to draw down. And right now it says I have 9.27 volts. So that means that between this point and this point, there's 9.27 volts potential to run through the circuit. Ohm's law, each resistor should consume or drop some of the voltage. So this part of the exercise will be to measure between the two halves of each resistor, between the anode and the cathode. Although resistors do not have anodes and cathodes, they are not polarity driven. We're referring to the most positive and the most negative side of that resistor. One thing that you may notice is that it makes it a lot easier to follow when all of the tolerances are in a row. So here I have my gold, my gold, my gold, and then these two are backwards. So when you're laying your circuit out, one thing you can do, especially if you're going to solder it for the next person, try to follow one regimen, then you don't get confusion. So let's begin by taking our measurements. So we're going to start with our first resistor, and this is the most negative half. This is the incoming source. So we're going to put our negative lead on the cathode side, if you will. And it's drawing down about 974.974 volts or 974 millivolts. So we're going to move to the next one and do the same thing. Again, we're going to move the black lead to the most negative part of the circuit. And that's taking 1.382 volts. So you're going to carry on doing the same thing for each pair of resistors and record the voltage. Now that you've completed that portion, we're going to look at the second tacit or function of the series circuit. and that is that the current flowing through the circuit should be the same throughout the circuit. There's only one path for the current to take. But to do this, we have to make a number of changes. First of all, on our meter, we can't leave it on volts. We have to put it onto amperage. So there is a setting for milliamps, but unlike measuring voltage, measuring milliamps is not possible by simply placing the two leads where we are going to detect our voltage. That's because we are putting the leads in parallel. And in order to measure any current of any circuit, you must put the meter itself in part of the current flow. You have to actually have it put it in the current stream. So we're going to change our settings to do that. Now you may notice at this point I've removed my black lead and I put the alligator clip back on. And right now it seems to be clamped onto the jumper that was on our red power bus. It's still plugged into the red power bus, but this is going to be the downstream, or if you want to consider it, the negative side of the flow. We're going to take our red lead, which is coming from the battery, and we're going to put this lead, the other alligator clip, on my red lead, so that now the way the circuit is working is the power is coming from my battery through the red wire into the meter itself. It goes into the meter reads the current, it comes out of the meter, in through the black lead, and then supplies current and voltage to the circuit, and then goes back through our black lead to return to the battery. Notice that I have this set for DC, not AC, and I have a reading of about 2.21 milliamps. For the next part of the lab, I have a bit of a problem. The lab calls for a second power source, but I only have my original battery available for my circuit. I do have, however, another 9-volt battery. So we're going to use a trick based on the series circuit. And that is, a series circuit can act as a voltage divider. I have 3 100 ohm resistors, and they're connected to another 9-volt battery. The 9-volt battery, when I tested it, was about 9.6 volts. Since I have 3 identical resistors, and since Ohm's law states that the sum of the voltage drops in a series circuit will always equal the incoming voltage, logic tells me that each of these should be 1/3 of the voltage. So if I use my tester and check each resistor, that's drawing 3.1 volts. That's drawing 3.125 volts. And the last one's drawing 3.11 volts. So the lab calls for the original 9 volts plus 5 volts. So if I were to take 2 of these in series, I get 6.22 volts, since each one is dropping 3.1 volts. So this means if I take a red lead from here at this juncture and a black lead from here, then between those 2 points, the same as where my lead is right now, I'm going to have 6.22 volts, which is slightly more than the lab calls for, but that gives me my second power source. Okay, so right now, the way I have this circuit laid out, I have my tester clamped on to the positive and negative of the circuit of interest. And I have the black of one battery going in and coming out on the red. Then the black of the other battery, the cathode, goes into the battery and comes out from the anode. And the total voltage is roughly 9 times 2, 17.72 volts. I don't need 17.72 volts, so we're going to use these resistors to reduce the amount of voltage by moving our cathode. So now I only have a single 100 ohm resistor in series, which is dropping the voltage by about 3 volts. Ideally I need 14, but let's just move it one more time. And put it in the right spot. And I've dropped another 3 volts. If I do it one more time, I'm down to 9 volts. Not quite exact because of the different voltage drops, and the batteries themselves are not stable. They'll constantly draw voltage. So in the lab, you're going to be putting 2 power sources in what they call an adding circuit. Because I put these in series, it's much like taking 2 battery cells and joining them together. If we were working on the lab itself, you're going to be doing 9 volts and 5 volts, roughly 14 volts. So this arrangement that I have with the 2 batteries and a resistor in the middle is giving me my 14 or 13.5 volts. Now that we have a larger power supply to work with, we can now go around and check the different voltages at the different resistors. I'm going to take my leads, my alligator clips off. Notice too that I put a small jumper on the negative one. It's not the same potential, but it acts as a good little test point. Okay, so now we can just go and check the voltage drop across each resistor. Where's my polarity? Silly rabbit. So the first one we have 1.43 volts, 2.3, 2.9, etc. So your job, because your voltage supply is different than mine, you do the same thing. Go around through each of these resistors and measure the voltage drop across each one. In the final portion of this lab, you will be required to determine whether or not half mount resistors will suffice in this circuit. You have 3 resistors, 40 ohms, 60 ohms, and 120 ohms, and they're all being fed with 15 volts DC. Recall from your electrical theory, you're going to need to calculate the total current, which can be found by dividing the total voltage by the total resistance. Determine whether or not the resistor can withstand current and voltage. You simply need to apply the Ohm's law that states that the power is equal to the current squared times the